Good morning. My name is Yutai Katoh from Oak Ridge National Laboratories. Let me start from thanking the organizers for this opportunity to talk about the emerging opportunities for the advanced ceramics and composites for nuclear energy at the occasion of the American Ceramic Society, European Ceramic Society joint symposium on the emerging ceramic technologies, challenges, and the future prospect at the MS&T 2020, the virtual meeting. Okay. Next slide. All right. I acknowledge the U.S. Department of Energy, Office of Nuclear Energy, and Office of Fusion Energy Sciences as the research sponsor. And also, I would like to thank my collaborators and the colleagues for the presentation materials and useful discussion, including Katirani, Takaaki Kuyanagi, Shinshan Fu, Vilna Geringer, and several other people too, inside and outside of Ridge. All right, so my talk is going to consist of the two sections. The first part is about the opportunity landscape in nuclear, and by saying nuclear, that it's the fusion energy and the fission nuclear energy. And the second part is going to discuss a few examples of those opportunities. All right, so in the fusion energy on the left side, you can see that I'm talking about the community consensus and the industry initiatives. On the nuclear side, they're talking about the advanced manufacturing and expedited the development qualifications, and also the industry initiatives. So the industry initiatives are the kind of the common elements between the fusion and fission. On the fusion side, starting from the community consensus, and this is actually important recent element of the opportunity landscape. The nuclear fission is a much more mature technology, as you all know, and where the materials and the fuels are established the most important R&D area, along with the reactor physics and thermal hydraulics sort of things. But for fusion energy development has been the reactor physics, pretty much 90% reactor physics. And the community started to agree upon that materials and the fuel cycles are really important to enable the fusion energy. So that's where we start this discussion. So the last year, or maybe end of the 2018, that DOE Office of Fusion Energy Sciences asked the American Physical Society to lead the community planning process on the long-range planning of the fusion energy and discovery plasma science development. So there's the pretty significant activity involving like 250 science leaders within the fusion community, trying to agree upon the priority research and development areas to enable fusion energy. So the community had like 3 full week the workshops discussing the priorities in the next 10 years for the fusion. The conclusions are summarized into this community plan report, which was presented to the Fusion Energy Sciences Advisory Committee, FISAC, in March 2020, and the fusion materials is one of the the 3 top level recommendations from the community to the FISAC. By the way, FISAC is the only body entity that can legally advise the DOE Office of Fusion Energy Sciences, about the research directions under the development. So the fusion materials, basically the recommendation is to expand the research in fusion materials technology, immediately begin design construction of the prototypic neutron source, which 14 MeV neutron source, to study the materials, expand the program for the development of structure, both the structure and the functional materials, and specifically target the investment on the blanket and the plasma facing component program, which means the materials for the breeding blanket and plasma facing components. So this is a very important the move for the fusion energy science. So once this FISAC in this ongoing the subcommittee, the planning activities concludes hopefully in this December, that the recommendation is hopefully translates into the actions by the development. Okay. Next one is the private industry initiatives. So the fusion energy is not going to make business in any near future, that everybody knows, but there are the increasing number of the startups which tries to develop the fusion energy. So this is a website from the Fusion Industry Association, and you can actually see the 22, if I count correctly, the fusion startups which are developing the own fusion energy concepts and possible, the proof of principle type reactors. In fact, that these fusion startups are raising the more capital, money than all the startups for the fission reactors combined. Recently, they have raised multi-billion dollars to develop the fusion reactors. The good thing about this is that each one of these startups are developing the innovative reactor concepts. They are out-of-box thinkers, and the innovative reactor concepts requires innovative component design, the components and the materials. So these are giving the opportunity for us to explore the innovative materials and designs. And there's a recent DOE emphasis on the private public partnership, PPP, which they assist, make the national lab assist to those startup industries. The program which was recently started, the pilot program, is called Infused, which stands for the Innovation Network for Fusion Energy. And so this pilot program is starting small, but the plan is to strengthen this program so that the DOE programs and these private industries initiatives can work together toward the developing fusion energy. So this is an Infused website, which should give them much more information about this kind of opportunities. If anybody is interested in this, in the materials area, please feel free to contact me, or of course, Dennis Hutchison of the ORNL, who is the director of the Infused program at ORNL. Okay. The next one is about mainly a fusion side. Of course, that fusion is also considering the advanced manufacturing. There are a few interesting activities starting. But this advanced manufacturing, mainly additive manufacturing or 3D printing, is becoming an important factor in the nuclear energy. So traditionally, the nuclear energy community has been extremely conservative and slow in adopting the new technologies, which is for a good reason. Because safety is of the paramount importance for the nuclear energy. So why do you take a risk when your existing technology is economically fairly competitive? However, the community cannot ignore the potentials of the advanced manufacturing. They enable the new materials, materials integration, components, and designs. They enable the new design space for the reactors. And they are even talking about the location-specific optimization of the materials within the component, and the operando NDE. May allow the bone qualified concept. Currently, that qualification of the material designs are taking a lot of time, which may be expedited if the bone qualified concepts kicks into the nuclear qualification process. The additive enabled nuclear material technologies they are being explored. I think that you have heard of the transformational challenge reactor TCR project as a pilot case of exploring the potentials of AM in building to enabling the new design concepts and how we build and qualify the novel nuclear reactor by utilizing the technologies enabled by the additive. So, and this TCR project is already posing the ripple effects to the commercially motivated innovative reactor projects. So there are few the innovative reactors commercially being developed, starting to adopt the AM technologies, which has developed in the TCR project. So I'll talk a little bit about this picture later. Okay. I guess that this is considered a slide within this first section. So the expedited development. So materials and fuels development has long been an extremely time-consuming process. Because of the development, both the development and qualification takes a lot of time. Think about the silicon carbide composite for nuclear applications. In 1999, that we developed the nuclear grade 6-6 composites. At that point, we knew that the 6-6 composite works in many of the nuclear applications, enabling the high temperature operations. However, it took 20 years for this material to be qualified. So that is the kind of time frame we're talking about for developing the new material, qualifying new materials, using the conventional the qualification route. If you look at the history, that the zirconium alloy fuel cladding, that was considered the fastest development of the nuclear materials in history. It took 20 years for the zirconium alloy to be fully developed. Okay, so the recent discussion emphasis within the nuclear fuels and materials community is that how we can accelerate the development and qualification by using the all the weapons we have, which is modeling and simulations, and the small the science-based the expedited experiment using the novel reactor experiment, plus that the neutron radiation and the radiated materials the examination is the obvious rate determining process, and how we the expedite this process is the main topic of the discussion, and the community is finding a way to do that, and they may eventually adopt that to the actual licensing process. So this will what this means to us is that the newer materials that the community and industries are more open to adopting the innovative materials, like ceramics for structures, for example. Okay. So the Office or DOE Office of Nuclear Energy is also actually that they did this a couple of years earlier before the fusion started the Infused program. So the DOE is now the actively engaged in helping the industries to explore and develop the new technologies using this GAIN program, which stands for the Gateway for Accelerated Innovation in Nuclear. So at the Idaho National Lab, there's a GAIN website which tells you what funding opportunities or the kind of the collaboration opportunities may be made available. The GAIN is a mechanism so for the National Lab to assist the industry. So it's essentially that Infuse and the GAIN are the very similar thing. GAIN is a bigger program for the fusion energy. Okay. All right, so I'm done with the first section. The second part is for the opportunity for advanced ceramics composite in fusion energy, and talking about a few examples. Going to talk about 6C composite, ceramic additive manufacturing, and additionally some functional materials and across the fusion, the current fleet, the nuclear energy, and the future, the nuclear reactor. Okay. Okay. So I'm talking about the 6C because the silicon carbide composite has is sort of the easiest example to talk about the advanced ceramics opportunity in the nuclear. So it's a sort of versatile materials, and it's useful, considered the useful for many reactors concepts or categories, including the fusion and light water reactors and the various generation 4 reactors. And each concepts are looking at the potential use of these advanced ceramics. But basically, the ceramic composite may be able to replace some of the structural materials used to be using metals, and expanding the temperature, service temperature range, which makes the reactor more attractive, the energy efficient, fuel efficient, and also that the radiation tolerance of silicon carbide may enable extended life. So there are economical benefit. And because inherently these are high temperature materials, so there's could be an inherent safety benefit of these materials. So there are reactor designs which assumes the use of 6C composite, particularly the high temperature gas-cooled reactors, the advanced reactor concept, which can use the 6C composite at any moment. The light water reactor, obviously, accident-tolerant fuels is a sort of a mid-term development. And for the Gen 4, other Gen 4 concept, basically that other than the supercritical water concept may possibly use the like the silicon carbide composites, right? So I think that I used essentially the same slide last year at an MS&T conference, so I didn't spend much time on this one. That the fusion blanket, this can benefit from the using 6 composite for the blanket, enabling high temperature operation of the lead lithium blanket, high dose radiation. This is a huge structure. This is about like 8 meters high component. So obviously the making these components, qualifying these, and make sure that these works without breaking. That's a challenge. Maybe an entryway for SiC composite for fusion is this flow channel insert application for the liquid metal blanket, which is not a structural materials applications, but it's a sort of the thermal and electrical barrier materials separating the hot liquid metal and structure. So there will be a significant thermal stress, which is usually the primary the loading to ceramic structure. So that still is a challenge. There are some, the ceramic composite is not necessarily the most attractive materials for the plasma-facing components, but there are design explorations using taking advantage of the advanced ceramics composite. This example is for the debater, using the SiC as the coolant channel materials, integrated with the tungsten plasma facing the component. But for ATF, guess that many people have talked about the accident transfuse, and for light water reactors and the SiC composites as the kind of the most attractive the option for cladding. Maybe a couple of core structure. The most attractive aspect of SiC composite is its slow kinetics of the oxidation in the high temperature steam environment. This, for example, this the SiC composite or silicon carbide inherently gives like by 3 orders slower oxidation kinetic compared to the zirconium alloy, which makes this particularly attractive materials. Okay, and there are additional benefits in the neutron potential high band gap. So, and as a market that this is, we're talking about the like 50,000 fuel rods times nearly 400 light water reactors operational worldwide, and fuel life 18 months. So this is the ultimate market size for this kind of technology. So each reactor core used like several tons of the cladding, silicon carbide cladding, if everything is made of the SiC composite for the fuel rod. I mean that the cladding. Right. The next Gen 4 reactors, as I said, that pretty much every concept of the advanced reactor concept may benefit from the adopting the advanced structural ceramics. And so some 15 years ago, these Generation 4 reactors are mostly concepts, and there are a few government the initiatives for the gas reactors or sodium fast reactors. The recent move is that the industries the spearheading in developing the advanced these Generation 4 reactors. I took a few examples. There are many other the private industry initiatives in exploring, developing the reactors, the mostly the small modular reactor type implementation, right? Every time we talk about the advanced ceramics and the composites for the generation 4 reactors, we are told that you need to have the design code. Otherwise, the designers have no idea how to use these composites for the nuclear. So we started this ASME's design code development for 6-6 and carbon-carbon composite in, we started the groundwork in 2004, and we have this little details here, but the quick the message is that in the 2019 the ACerS section 3 design code, boiler and pressure vessel design code started to include the subpart on the composite materials within this the high temperature, where is it? The section 3 division 5, which is the high temperature reactor design code. And this defines the material, how to design the reactor, high temperature reactor component using the 6-6 and carbon-carbon composite. Obviously, the 6-6 composite is for the component which receives the significant neutrons. And the carbon-carbon composite is for the components which does not receive too much neutrons, but it needs to withstand the very high temperatures, high stress, sort of thing. Okay. Additive manufacturing, I guess I have 3 minutes remaining. So basically these advanced ceramics like silicon carbide is extremely attractive in terms of the intrinsic properties, but difficult to use. If you have the advanced manufacturing techniques like this, the AM shaping of complex geometries and features, or you can build the fibers in any configurations, directions, or kind of the print it in the net shape in any architecture you want. That is sort of the breakthrough. So the details are discussed in recent paper by Takaaki Kuyanagi, so I defer to that paper, but this it's presenting tremendous opportunities. This TCR is a great example of implementing the IAM for advanced reactors. So in this is a small reactor, and but the core and many components are made of AM, metals or ceramics, and particularly the fuel element is made of the additively manufactured silicon carbide with the trisul fuels incorporated in the complex the element, and it also uses the hydride modulator incorporated into the fuel assembly unit, which is a unique feature of this concept, which is enabled by the manufacturing. So this AM of silicon carbide combining the binder jetting and the CBI is documented by Katoh in the recent Journal of the American Ceramics Society article. Okay. This AM silicon carbide is of very high quality. It's a fully crystalline and proved to be radiation resistant. The strength, if you look at the strengths that it's enabling, like the Weibull modulus 14, 15, which is much higher than the conventional CVD silicon carbide, monolithic silicon carbide. And again, that because of the high crystallinity and the stoichiometric nature, that this material is highly radiation resistant. Finally, I want to talk a little bit about what is going on. The hydride. So hydride, it's I don't know if people call it ceramic. To me, it's ceramic because by definition, this metal hydride is the inorganic non-metal. The hydrogen does the covalent bonding with the metallic lattice. So this advanced moderator has been developed to enable this the TCR concept. So this development by the Xunshan Fu of ORNL, basically the crack-free, high hydrogen density. Hydrogen has a high density as high density as like a liquid hydrogen in this metal hydride. So this is a very effective moderator for neutrons, and also it can be used as a kind of the neutron shielding in the fusion reactor too. And so this is another example of the novel ceramics may renew the nuclear technology. And also another aspect of this is that metal hydride will release hydrogen, and if it's depleted with hydrogen, it's not a moderator anymore. So it requires the cladding. And cladding, of course, that to contain hydrogen, that ceramics like alumina, silicon carbide are some of the most effective the permeation barrier for against hydrogen. And the containing these hydride in ceramics, requires the high temperature, which is the problem. So again, the using the additive manufacturing techniques may be extremely useful to make the ceramic cladding for these the novel the functional materials. So this is my kind of the last slide. So the take-home message is first, the opportunities for advanced ceramic composite in the nuclear energy, expanding across the fusion current-free thermonuclear and advanced fusion reactor systems. In this opportunity landscape, the commercially motivated initiatives, advanced reactor development, are playing the significant roles in exploration of the advanced concepts, design, components, and materials across both the fusion and advanced fusion energy systems. And finally, that rapidly advancing the additive manufacturing technologies are enabling the utilization of advanced ceramics that possess the inherently attractive properties. So that's my last slide. I apologize that I spent 33 minutes. So any questions, comments, I'd like to, anything that please email me, or I'll be happy to discuss. Thank you very much again for your attention.